We have seen linear regression for a bit in the first lecture, where we tried to predict the number of umbrellas sold based on the rainfall. Let's explore linear regression a bit more. Linear regression is a simple machine learning method that you can use to predict an observation's value based on the relationship between target variable and the independent linearly related numeric predictive features. For example, imagine you have a dataset that describes key characteristics of a set of homes like land acreage, number of stories, building area, and sales. Based on these features and the relationship with the sales price of these homes, you could build a multivariate linear model that predicts the price of a house that it can be sold for based on its features. Linear regression is a statistical machine learning method that you can use to quantify and make predictions based on relationships between numeric variables. There are two main types of linear regression. One, simple linear regression, and the other, multiple linear regression. Simple linear regression is where you have one predictor and one predictant. Multiple linear regression is where you have multiple predictors but only one predictant. I am going to show you how to do both of these in the coding demonstration. In terms of use cases, linear regression is used for sales forecasting, resource consumption forecasting, as well as telecom service lifecycle forecasting. Of course, there is a wide variety of use cases for a linear regression, and these are just a few. And in terms of assumptions that linear regression makes on your data, linear regression assumes that all variables are continuous numerical, not categorical variables. It assumes that the data is free from missing values and outliers. It assumes that a linear relationship between predictors and predictant occurs, and that all predictors are independent of each other. Lastly, it assumes that the residuals are normally distributed. Don't worry too much about all this if you don't understand, because I am going to show you how to look at your dataset and test whether it meets the assumptions, and that's coming up in the coding demonstration. The first type of linear regression we are going to do is a simple linear regression. The first thing we need to do is import our libraries in cell 1. So we'll import numpy as np, pandas as pd, and we'll be using the matplotlib. So I'll import matplotlib.pyplot as plt. And then we are going to use the scikit-learn. So we'll import sklearn. Next, we need to be able to set our plotting parameters. So from pylab, we are going to import rcparams, and then from sklearn, we need to import the linear regression model. So to do that, we say from sklearn.linearModel, we want to import linear regression, and then from the sklearn preprocessing, we need to import the scale function. So we do from sklearn.preprocessing import scale. Okay, so now that we have all the libraries inside of our Jupyter notebook, let's move to cell 2. And here we are going to set the plotting parameters. So we want matplotlib to plot out inline within our Jupyter notebook. So we say %matplotlib inline, and then we'll just set our dimensions for our data visualizations to be 10 inches wide and 8 inches high. So we'll do rcparams, and then we'll just write a string figure.figsize is equal to 10 by 8. So now coming to cell 3, we are just going to create some synthetic data in order to do a linear regression. Let's create a variable called rooms, and we are going to set rooms is equal to 2 times a set of random numbers. So we are going to need to call the random number generator, which is going to be np.random.randn, and then we'll pass in how many values we want. In this case, it will be 100. So here's the equation that we are going to use to generate random values to populate the rooms field, or basically to create a synthetic variable that represents the number of rooms in a home. So let's just print it out and see what it looks like. So to do that, we'll just say rooms and we'll print out the first 10 records. So 1 to 10. So one thing to note here is that the numbers on your machine will look different than mine, and that's just because we did not set the seed for the random number generator, and that's totally fine. There is nothing wrong with that. And this is what happens if you don't set the seed for the random number generator. So now coming to cell 4, we will create a synthetic variable called price, and we'll say price is equal to, here's the equation that I came up with to create a synthetic representation of price. That's 265 plus 6 times number of rooms plus the absolute values, and we need to use the ABS function for that, the absolute value of, and we are going to call a random number generator, so that's np.random.randn and 100 values. And now we want to just take a look at the first 10 records, so we'll say price 1 through 10. So now when we run this, again we are going to get a set of numbers, and you might be getting some different numbers that are exactly not same as mine, and that's because we didn't set the seed for the random number generator. So don't worry about it, it's not a problem. Now let's create a scatter plot for our synthetic variables to get an idea what they look like and see the relationship between them. So let's move on to cell 5, and we are going to call the plot function, and that's plt.plot, and we'll pass in rooms and price, and price is going to be on our y-axis and rooms is going to be on our x-axis. Let's also pass a string that reads r hat. This specifies that a point plot should be generated instead of a default line plot. So now we'll create some labels for our x-axis and for our y-axis. So for our x-axis label, we need to say plt.xlabel, and then we'll pass in a string that reads number of rooms 2019 average. And then we'll also create a label for the y-axis. So that will be plt.ylabel, and we'll pass in a string that reads 2019 average home price. And that's going to be in thousands of US dollars. So now let's see what this plot looks like. We'll call the show function, which is plt.show. Alright, so even though your random numbers are slightly different than mine, you will be able to generate a plot that looks like this. And you can see that there is a linear relationship between the variables and that they are continuous. You can tell that by just looking how the data points plot out against one another in terms of distribution as well as trend. What this is saying that as the number of rooms increase, the price of the house increases. That totally makes sense, right? So now let's do a simple linear regression in cell 6. So for our model here, we are going to use rooms as the predictor. So we are going to say x is equal to the number of rooms, and we want to predict for the price. So y is equal to the price. Let's instantiate a linear regression object, and we'll call it linreg, and then we'll say linreg is equal to linear regression, and we'll fit the model to the data. So to do that, we'll say linreg.fit, and we'll pass in the variables x and y. So first things first, let's print out the intercept and estimated coefficients for the model. We do that by just calling the print function and passing linreg.intercept and linreg.coefficient. Alright, and once you run this, you're going to get numbers that are almost as identical on the screen. So you should get something that reads 265 for your intercept and something like 5.9 for your coefficient. Now let's take this step back to simple algebra. You would have learned in middle school probably. The equation for a simple linear regression is y equals mx plus b, where b is the intercept. So in this case, our intercept is 265.7 and our coefficient is 5.99. 5.99 represents the estimated coefficients for the terms in the linear regression problem. So now let's take a look at how well our model performed. And to do that, we call the print function and we'll generate a score of the linear regression model. So we'll say linreg.score and we'll pass in the variables x and y. The score function returns the coefficient of determination, that is R squared of prediction. In this case, we are getting 0.974 and you should be getting something very similar at home. So our linear regression model is performing really well and our R-squared value is close to 1 and that's a good thing. But I want you to note that each time you run this code, you will be getting a slightly different R-squared value, and that's because when we created our dummy data, we didn't set the seed for the random number generator. So don't worry about it that your results might be slightly different. It's totally fine because the model is working the same. It's just that the input data is slightly different. So now this was a very basic example of simple linear regression. Now let's take a look at how to do the multiple linear regression. Alright, so let's do some multiple linear regression. So as earlier, we are going to use NumPy, Pandas and Matplotlib as well as scikit-learn in cell 1. As I've already gone ahead and set the plotting parameters for your Matplotlib in cell 2. Now coming to cell 4, the only thing that I want to add here is that we are going to use Seaborn, and so we are going to import Seaborn as SB, and also we need to set the style for Seaborn. So we are going to say sb.setStyle white grid. Lastly, we need to import our counter from collections. So we'll say from collections import counter. Now let's create a data frame for our enrollment data in cell 5. We are going to call that enroll and we are going to use the pd.readcsv function. And then we just need to name the columns for the enrollment data. So we'll say enrollment.columns and we'll set that equal to a list of column names which are going to be year, role, unem, hgrad and inc. So now we'll say enroll.head. Just so you know, this data has been taken from New Mexico and it starts at year 1961. So year 1 is actually 1961. Role indicates the enrollment numbers. Unemployment indicates the local unemployment in that year, and then hgrad is the graduation rate, and then income is the local income in the region during that year. Now according to the assumptions of the linear model, our variables all need to be continuous numeric variables. We need to make sure that there is a linear relationship between the predictors and the predicant. So let's check for the correlation in cell 6. To do that, we'll use Seaborn and we'll say seaborn.pairplot and we'll pass in the enroll data and run this. So here's our scatterplot matrix, and let's look at some of the relationships between some of our variables here. So we'll start by looking at the relationship between unemployment and enrollment. So you could say that maybe there is a linear relationship of some sort here, but it could be a little bit stronger. But we are just going to call this good enough and see how unemployment does as a predictor anyway. Now let's look at the hgrad and enrollment linear pair. So the relationship between hgrad and enrollment actually looks pretty good. They are definitely in a linear relationship. We also need to make sure that these variables are continuous numeric variables, which just looking at the distribution you can tell that they are. We need to check the correlation. So to do that, in cell 7, we are going to draw on what's called the Pearson correlation coefficient. We are going to call the core method of our enrollment data frame. And once we print this, we just want to make sure that our predictors are not completely dependent on one another. And then we print this out. We just want to make sure that our predictors are not completely dependent on one another. That would definitely not be good for a linear regression. So let's look at the hgrad and unemployment correlation. And we see that the hgrad variable and unemployment are definitely not showing linear correlation. And that's good news. So in cell 8, let's just try those two out and see how they do as predictors with a linear regression model. The first thing we need to do is create a subset, and we'll call that enroll data, and we'll set that equal to, and we'll just select our enroll data frame, but we only want the unemployment, so that's unem and hgrad variable. and of these we only want the values, so we'll call dot values. And then let's also set a target here, so we'll call that enroll underscore target, and we'll set that equal to our enroll data frame, but we only want to select the role variable here, and we'll say dot values, and then let's set some names for our data. So we'll create a variable called enroll underscore data underscore names, and we'll set that equal to, and then we are going to say unem and hgrad. And of course, before using our variables as predictors in a linear model, we should scale them. Our predictors are going to be x data, and then our target is going to be y data. The next thing we need to do is, as per the model assumption, is check for missing values in cell 9. So let's just use some basic filtering to do that. We'll filter them out and see if anything comes up. So let's create a variable here called missing values, and we are going to set that equal to x. Here x is equal to not a number, so we are going to say that it's equivalent to np.nan. That's not a number from NumPy library. And then let's just filter these out. So we are going to then call our x dataset, and then we want to print out where we have missing values from that data. So we are going to say print out the missing values where missing values comes up as equal to true. And then we get back an empty array, which means we have no missing values, and that's perfect. So the next thing that we need to do is instantiate a linear regression object. So we are going to call it linreg, and we are going to say linreg is equal to linear regression, and then we want to say normalize is equal to true. This tells linear regression model to normalize our variables before regression, and then let's just fit this model to our data. So to do that, we are going to call the fit method of it. We are going to say linreg.fit, and we'll pass in our data, so x and y, and then let's just print out a score for how well our model performs. So we are going to call the print function, and then we are going to access linear regression model, and we are going to ask for a score and pass in the variables x and y. And once we run that, we see that we get 85%. Now the score that's printed out here is the R-square of the prediction. It's a measure of how well the regression line was predicted by the model actually matches the real values for college enrollment. Basically, it is telling us how well the model performs in predicting college enrollment. A maximum good score would be 0.99 and a minimum score would be 0.01. If you see a value of 0 or 1, you know something is wrong with our model. So this model has an R-squared value of 0.84, which isn't too bad. Of course, this could be better, but this is a fast demonstration of linear regression. Now let's move on and talk about association rule mining and a priori algorithm. So association rule mining is a process that deploys pattern recognition to identify and quantify relationships between different yet related items. Association rules help us answer questions like, if you buy milk and eggs, you are more likely to buy bread than anyone else who did not buy milk or eggs. Association rules seek to find relationships between purchases made by customers. This is a very important tool for supermarkets and online stores for replacement of products and recommendations of products for existing or new customers. Say for example, eggs and bread are frequently purchased together. With that finding, you can increase sales by 1, placing eggs and bread together next to one another, so that when a customer buys one of the products, he doesn't have to walk a long way to buy the other product. Or 2, advertising to the buyers of either eggs or butter in order to increase that person's propensity to purchase the paid product. Or 3rd, you could offer discounts on both eggs and butter if the customer buys both of them in one purchase. Now that you have an understanding of what association rules are and how they are used to generate business value, let's go ahead and take a look at how to express these as an association rule. For example, if item X are purchased, then the possibility of buying bread is. Association rules offer several advantages. Those include it's a relatively fast method, works well on small quantities of data, and doesn't require much feature engineering. This is the first time we've talked about feature engineering, so let me define it for you. The term feature engineering refers to the process of engineering data into a predictive feature that fits the requirement and/or improves the performance of a machine learning model. There are three main ways to measure association. Those are support, confidence, and lift. Let me support the definition of each of these terms by supporting them with an example from the bread and eggs analogy. Suppose there are 5,000 transactions in a supermarket data and bread was sold 500 times, whereas eggs were sold in 350 transactions. There are 150 transactions where both bread and eggs were purchased together. In this dataset, A would be bread purchases and A would be equal to 500 transactions. C would be eggs and the number of eggs purchases, which is 350 transactions, and the number of times that both bread and eggs were purchased equals 150 transactions. Now support is the relative frequency of an item in the transaction data. It basically expresses how popular the item is as represented by its proportion of the total items sold. So in our example, support for bread can be calculated as 500 divided by 5000. A divided by the total number of purchases, which is 500 divided by 5000. So the support for bread would be equal to 0.1. Now confidence is the probability of seeing the consequent item, in other words, the then term of the equation within the data, given that the data also contains the antecedent, the if term. In other words, confidence tells you how likely it is for one item to be purchased given that the other item is purchased. Confidence determines how many if-then statements can be found to be true within a dataset. Using the bread and butter example, the likelihood of buying eggs when bread is bought is calculated out to be 30%, meaning that there is a 30% likelihood that eggs will be bought when bread is bought. We generated that number by first calculating the proportion of transactions that were both bread and eggs. So that's 150 transactions divided by 5000 total transactions. So that goes in the numerator, and then we divide that by the proportion of transactions that were bread alone, which of course is 500 transactions divided by 5000 total transactions. When we do the math, we come out to 0.3 or a 30% likelihood that eggs will be bought when bread is bought. Now lift is a metric that measures how much more often the antecedent and consequent occur together rather than having them occur independently. I'll show you how to work this equation in just a second. Let me explain lift scores real quick. If you get a lift score greater than 1, it means that A is highly associated with C. In other words, if A is purchased, it's likely that C will also be purchased. If you get a lift score of less than 1, then you can conclude that if A is purchased, it's unlikely that C will be purchased. If you get a lift score equal to 1, this indicates that there is no association between item A and C. So going back to our example, let's calculate lift. To do that, we need to divide confidence by support. We already calculated the confidence back here, and we found that there is a 30% likelihood that eggs will be bought if bread is purchased. Our confidence is 0.3, so we put that in our numerator when calculating lift. Then we need to divide that by the support of C. We've already calculated that support when we were looking at the example. And you see here that we have a support of eggs actually 0.07 or 350 divided by 5000. It's the proportion of eggs purchases of the total number of purchases made. So we just plug that into our lift equation, and when we do the math, we get a lift of 4.28. Now a lift score of greater than 1 means that A is highly associated with C, meaning that if A is purchased, it's likely that C will also be purchased. So your rule would come out as, if a customer buys bread, then they are likely to buy eggs also. Now where does a priori fit in? A priori algorithm is the algorithm that is used to implement the association rule mining over structured data. So here we are in our Jupyter notebook for association rule mining with a priori. So I'm making the assumption that you got the Jupyter notebooks by installing Anaconda, and in that case you will need to do a pip install. So in cell 1 we do a exclamation pip install mlextend, and we need to install this mlextend library. Then we need to import our libraries in cell 2. In this demonstration we are going to import pandas as PD, and then from our mlextend we are going to import the a priori algorithm as well as association rules. Now once you run that, you will have your libraries, and then let's read in our data in cell 3. It's really important to get the data in the right format. Transaction data needs to be in sparse format for the association rules. So it's often not in that format that we need. So it's often not in the format that we need it to be in. So we have to convert it, and I am going to show you how to do that. Let's just read in the data first and then look at the first 5 rows. So what we are seeing here is that there is that each row is a transaction, and so we are seeing 5 transactions in the output of cell 4. Now this data needs to be converted to the sparse format so that a priori algorithm can work on it. So we can convert our data by using the getDummies function from the pandas package and then implement one-hot encoding. You had seen one-hot encoding back in lecture 1 also, where we had converted the male and female values to 0 and 1. So in cell 6, let's take a row. Then in cell 6, let's take a look at the head here. So we are going to say baskets.head. Now this above snippet is basically the transaction data from the grocery store. The items are all listed along the columns, and then each transaction is represented by a row. Now as you recall, support tells us how popular an item is based on the proportion of all the transactions that include it. So in cell 7, let's start by taking a look at the items that have a minimum support of at least 0.02. So we'll call the a priori function and we'll pass in our data set, basket sets, and then we'll set the minimum support equal to 0.02. And when you run this, and on running this, you will get the data here. So as you can see, you have 35 items with a support of 0.02. With a support of 0.02 or above. But unfortunately, this table has item indices and not the item names. So we want to get an idea of what these items actually are. So let's generate a column that actually gives us the names of the items that were purchased. So in cell 8, we'll take the same code and pass in another parameter that reads use column names equal to true. And once we run it, we can see that we have our item set names here. It's better that we are actually going to see which is the popular items that we purchased from the store. Now that we have our item set names here, it's better, but now that we have our item set names here, it's better. But what we are actually seeing here is the popular items that are purchased from the store. These aren't combinations of items, so it doesn't really help us that much from a marketing purpose. So let's decrease this support value, and since the support is 0 and since the support of 0.02 is only returning single popular items, and when we decrease support, we should be opening up our list so that we can explore more popular combinations of items. So in cell 11, we'll create a new data frame called df, and we'll set it equal to our basket set, and this time we are going to set support equal to 0.002, and then I'll call this output frequent item sets. Let's also add in a column here that describes the length of the combination so that we can see where one item is being sold, has a length of 1 and 2 items will have a length of 2, and then we'll just print out our frequent item sets. So this is how the dataset looks. So now if you see the output of cell 11, we had a lot of different items and combination of items to consider, but still we are seeing all of these, one item purchases, which isn't that useful for our analysis. So let's just filter these out where we can have only item combinations of 3 or more. So to do that, let's go to cell 12. And here we are going to create a filter where length is greater than 3. So what you are seeing here are the combination of 3 items that are frequently purchased together. Now let's use these to generate some association rules in cell 13. It's actually quite easy to generate association rules with this MLExtend library. The argument to generate rules takes 2 inputs. One defines if the metric should be confidence or lift, and the other sets the minimum level for these metrics. So we'll look at confidence first. Let's try building some rules with confidence levels as the metric, and the minimum support and the minimum threshold level of 0.5. So we'll say rules is equal to, and then we'll call in the association rules function, association rules, and pass, and then we'll call our association rules function, association rules. We'll pass in our frequent items dataset, and we need to define in a parameter that says metric is equal to confidence and minimum threshold is equal to 0.5. And then let's just take a look at the first 5 records. So as can be seen from the output, the minimum confidence level starts at 0.5. Remember that confidence tells us how likely it is for one item C to be purchased given that the other item is purchased, the A item. So if we look at row 0 here, we can see that we have a confidence score of 1. It means that if sausage is purchased, it's extremely likely for a frankfurter to be purchased in the same transaction. Now let's create rules with lift as the metric in cell 14. And we will keep the minimum threshold of 1. Now remember that lift tells us how much more often item A and item C occur together in the same transaction as opposed to being purchased in separate transactions from one another. In other words, instead of occurring independently. Now looking here at this data, we can see 5 possible combinations of items purchased together. The combination with the greatest lift of these 5 is beef and citrus fruits. Although row 0 and 1 both list this combination, row 1 has a slightly greater confidence. This leads me to think that there is a slightly more valid prediction. This leads me to think that it is a slightly more valid prediction to say that if citrus fruits, in other words item A, is purchased, then beef will likely be purchased, where beef is item C. Yes, you could say that if beef were purchased, then it's likely that citrus fruit. Yes, you could say that if beef were purchased, then it's likely for a citrus fruit. It's likely for a citrus fruit to be purchased, but there is slightly less confidence in this prediction. Now that we have generated rules, let's filter out these rules for optimal lift and Let's filter out these rules for optimal lift and confidence in cell 15. So from our above rules data, we want to create a filter that selects only Now that we have generated rules, let's filter out these rules for optimal lift and confidence in cell 15. So from our rules data, we want to create a filter that selects only rules with a lift greater than 5, and we also want to have a confidence greater than 0.5. So we only want the rules with a value of greater than 0.5 in the confidence field, and we'll print this out. We still have a lot of transactions here. So there are 76 combinations that meets this requirement. Let's just have a look at one of them. Now you can see here at row number 7. Now you can see here at row index position 779 that if whole milk, in other words item A, is purchased, then it's very likely the other vegetable will also be purchased in the same transaction, where other vegetable is item C. We know this by looking at the lift and confidence of this unique combination. So if you look at the lift here, it's equal to 12.97. This indicates a high likelihood that C will be purchased in the same transaction if A is purchased. In other words, a high likelihood that the other vegetable will be purchased in the same transaction if milk is purchased. And looking at the confidence, we have a value of 0.92, indicating a high degree of confidence in this prediction. You can use this exact method to start making recommendations for products that should be stocked up and placed nearby one another in a store. You can use this exact method to start making recommendations for products that should be stocked up and placed nearby one another in a store. Now let's move on to k-nearest neighbor classification. So k-nearest neighbor classification is a supervised machine learning method that you can use to classify instances based on arithmetic differences between features in a labeled dataset. In the coding demonstration for this segment, you are going to see how to predict whether a car has an automatic or manual transmission based on its number of gears and carburetors. K-nearest neighbor works by memorizing observations within a labeled test set to predict classification labels for incoming unlabeled observations. The algorithm makes predictions based on how similar training observations are to the new incoming observations. The more similar the observations values, the more likely they will be classified with the same label. Popular use cases of k-nearest neighbor include stock price prediction, credit risk analysis, predictive trip planning, and recommendation systems. So now we need to look at the k-nearest neighbor assumptions. So the k-nearest neighbor model assumes that your dataset has little noise, that of course it's labeled, that your dataset only contains relevant features, and that the dataset has distinguishable subgroups. You also want to avoid using k-nearest neighbors on large datasets because it's probably going to take a very long time depending on how big your dataset actually is. So let's use Python to implement the k-nearest neighbor algorithm. So here we are in the Jupyter notebook, and we import all the packages and import k-nearest neighbors classifier in cell 7 and cell 8. Then in cell 9, we have the settings that you need for printing out our data visualizations. You don't need to worry about them, just run them. And in cell 10, we have read the data and provided the column names for our empty cars dataset. Then we need to create a data frame called x prime, and we'll set that equal to our cars dataset. But then we only want to isolate out a small subset of that dataset. So we are going to be working with mpg variable, which is miles per gallon. We are going to work with displacement or disp. We will use HP or horsepower, and then finally we'll use weight or WT. So now we want only the values over here, so we are going to say dot values. So our target variable, of course, is going to be automatic and manual transmission. So that's the AM variable. So we will use iLock on cars in order to select that column. And we want to select that column at index 9. And we only want the values. So we are going to say dot values. Now before we implement the k-nearest neighbor algorithm, we need to scale our variables in cell 11. We actually do this to satisfy the assumptions of our model. It's always important to do that. So we will use the scale function from pre-processing module of scikit-learn, and we'll pass in x prime, and that scales our variables. Now in cell 12, I'm going to split the data into test and training sets. We'll use the training set for training the model and the test set for evaluating the model's performance. So to do this, we are going to just call train test split function, and then we'll pass in our data. So that's going to be the x and y, and then let's make it 20% of our overall dataset size. So we'll say that test size is equal to 0.2. And in this case, in this demo, we'll set a random state equal to 17. And so you will get the same results on your machine as I'm getting on mine. So what's this function going to output is that it's going to output our x training data, and we'll call that x train, our x test data, and we'll call it x test, and our y train data and our y test data. Now it's time to build the model in cell 13. The first thing we need to do is instantiate a classifier. We'll call it CLF, and then we are going to set that equal to neighbors.kneighbors classifier, and that's the function in scikit-learn, and then we are going to call the fit function and pass in our data. So that's going to be clf.fit, and then we just print out our model so we can get an idea of the default model parameters. So we'll do print CLF. So these are our default parameters, and now let's go ahead and evaluate the model predictions. So in cell 14, we'll generate a test point and we'll call it ypred. So we are going to say ypred is equal to, and then we'll call the predict function. And then our expected values are actually our ytest data. So we'll just say yexpect is equal to ytest, just to make it a little more human readable. Now let's go ahead and use the classification report function in order to evaluate how well the model has performed. And within that classification report, we are going to pass the data that we want to use for the evaluation. So that's going to be yexpect and ypred. And then we just want to print out the whole thing, so I'm going to use the print function on this whole thing. So as we can see in the cell 14 output, we've got a decent performance here. So these are the results from the demonstration we just did, and I just want to explain them real quick. So recall is a measure of a model's completeness, and that's what these results are saying, is that of all the points that were labeled 1, only 67% of those results that were returned were truly relevant. And of the entire dataset, 83% of the results that were returned were truly relevant. High precision and low recall generally means that there are fewer results returned, but many of the labels that are predicted are returned correctly. In other words, high accuracy but low completion. It's time to take a look at decision trees with classification and regression. First, let's start with what's a decision tree. A decision tree is a decision support tool that models decisions in order to predict probable outcomes of those decisions. Decision trees are comprised of three types of nodes. Those are root node, decision node, and leaf node. A root node is a node that represents the entire population or sample, and this gets divided into two or more homogeneous sets. A decision node is where subnodes split further into subnodes, and a leaf node is just the end node or the furthest subnode. It doesn't split. Here's the anatomy of a decision tree. So the topmost node is a root node, and then each of the subnodes where we have the splitting going on, those are our decision nodes. And then down here we have our leaf nodes. So leaf nodes are the end nodes. They are leaves of the tree, the very end point of the tree, whereas the root is the base. Now let's look at decision tree algorithms. These are a class of supervised machine learning methods that are useful for making predictions from non-linear data. Decision tree algorithms are an appropriate fit for continuous input and or output variables as well as categorical input and output variables. There are mainly two types of decision trees. Those are categorical variable decision trees and continuous variable decision trees. Now we already talked about classification trees and regression trees. So the classification tree is categorical variable decision tree. And this is when you use a decision tree to predict for a categorical target variable. The regression is the continuous variable decision tree. And this is when you use a decision tree to predict for the continuous target variable. There are several benefits to using decision trees. Those are decision trees are non-linear models, hence they can fit the data even if it's non-linear. They are very easy to implement. It's often said that decision trees mirror human thinking and hence they have better interpretability than other regression and classification methods. These trees can be graphically represented in a way that's very easy to read and very easy to interpret. Lastly, decision trees require less data preparation. It's also nice that they take care of categorical variables without having to implement one-hot encoding. So decision trees are not without their assumptions, of course. Those assumptions are that the root node comprises the entire training set. Predictive features must be either categorical or if they are continuous, they have to be built prior to model deployment. Lastly, decision trees assume that the rows in the dataset have a recursive distribution based on the values of attributes. Now let's take a look at how decision trees actually work. In the first step, decision trees deploy recursive binary splitting to stratify or segment the predictor space into a number of simple non-overlapping regions. In the second step, they make a prediction for a given observation by using the mean or mode of the training observation in the region to which it belongs. And lastly, in the third step, they use a set of splitting rules to summarize the tree. At every stage, we split the region into two, and we do this by implementing something called as recursive binary splitting. Recursive binary splitting is the process that is used to segment a predictor space into regions in order to create a binary decision tree. Recursive binary splitting stops when user-defined criteria are met. How recursive binary splitting works is at every stage we split the region into two, and we do this by the following criteria. In regression trees, we use the sum of squares to calculate the loss function, thus identifying the very best split. But in classification trees, we use the Gini index to calculate the loss function, thus identifying the best split. The recursive binary splitting approach is top-down because it begins at the top of a tree, at which point all observations belong into a single region, and then successfully splits the predictor space. Each split is indicated via two new branches further down on the tree. It is greedy because at each step of the tree building process, the best split is made at that particular step rather than looking ahead and picking a split that will lead to a better tree in some future step. Decision trees have their disadvantages. They can be very non-robust and sensitive to training data. What this means is that a small change in the training data can cause a large change in the final estimated tree. Since we are using a greedy approach while training the decision trees, it can't be guaranteed that the procedure would get us the global optimal tree. One way to tackle this is to train multiple trees where the training data and the features are randomly sampled. Let's take a look at where it's appropriate to use a regression tree. Regression trees are appropriate when the target is a continuous variable and there are linear relationships between features and target. Now what you would know is that output values from terminal nodes represent the mean response and values of new data points will be predicted from that mean. Let's take a look at the mechanics behind recursive splitting in regression trees. At every stage in regression tree, the region is splitting into two according to the sum of square errors. The model begins with the entire dataset S and searches every distinct value of every predictor to find the predictor and split value that partition the dataset into two subgroups, S1 and S2, such that the overall sum of square errors are minimized. Turning now to using decision trees for classification, classification trees are appropriate when your target is binary, that is categorical variable. Now, what you should know is that the output values from terminal nodes here represent the mode response and values of new data points will be predicted from that node. Let's take a look at the mechanics behind recursive splitting in classification trees. At every stage in a classification tree, the region is split into two according to a user-defined metric, for example, the Gini index. This is a measure of total variance across the K classes. It measures the probability of misclassification. Now another important term that you need to know in decision trees is tree pruning. Tree pruning is the process that's used to overcome model overfitting by removing subnodes of a decision tree. In other words, replacing a whole subtree by a leaf node. Now why do you need to prune a decision tree? Well, if you grow a tree deep, it would make good predictions on the training data, but it will probably lead to bad performance on the test data. That's because of overfitting. In these cases, you need to prune the tree. The subtree in question is replaced by a leaf node if a decision rule establishes the expected error rate in the subtree is greater than the single leaf. Two popular tree pruning methods include holdout test and cost complexity pruning. Holdout test is the fastest and simplest pruning method. With this method, you work through each leaf node in the tree and evaluate the effect original removing it using a holdout test set. A leaf node is removed only if removing it results in a drop in the overall cost function on the entire test set. You stop removing nodes when no further improvements can be made. Cost complexity pruning is also called the weakest link pruning. This is where a learning parameter alpha is used to weigh whether the nodes can be removed based on the size of the subtree. Now let's move on to naive Bayes. So naive Bayes classification is a machine learning method that you can use to predict the likelihood that an event will occur given evidence that's supported in a dataset. For the demonstration in this section, we are going to build a naive Bayes classifier from our large dataset of emails called spam base. Some of these records in the dataset are marked as spam. All the other records are marked as not spam. Predictive features in this dataset serve as our evidence. Using them, we can build a spam filtering system with naive Bayes model and successfully predict which incoming emails are spam and which are not. Now, as I said, naive Bayes is a machine learning method that you can use to predict the likelihood that an event will occur, given evidence that's present in your data. In the world of statistics, this is called conditional probability. There are three types of naive Bayes model. Those are multinomial, Bernoulli, and Gaussian. The multinomial naive Bayes is good for when your features are categorical or continuous and describe discrete frequency counts. The Bernoulli's naive Bayes model is good for making predictions from binary features. Lastly, the Gaussian naive Bayes model is good for making predictions from normally distributed features. So the use cases for naive Bayes include spam detection, customer classification, credit risk prediction, and health risk prediction. In terms of the assumptions of naive Bayes model, naive Bayes assumes that your predictors are independent of each other. It also holds an a priori assumption. This assumption is that past conditions still hold true. Basically, when we make predictions from historical values, we will get incorrect results if present circumstances have changed. A little note that I wanted to add here is that actually all regression models maintain an a priori assumption. So now let's see the Jupyter notebook for this demonstration. So we will be using the Gaussian naive Bayes, Bernoulli naive Bayes, and multinomial naive Bayes from the naive Bayes module of scikit-learn. And after importing all the relevant libraries in cell 3 and 4, we'll come to cell 7. And in this demonstration, we are going to be using the spam Bayes dataset. This dataset actually comes from the University of California in Irvine. And we'll just import the dataset using the URL. To do that, we'll need to import the request module from URL lib. And then let's create a new dataset called raw data. And this is going to be the data that we read in from UC Irvine. Now we want to treat this dataset like a comma separated file because that's what it is. In order to do that, we'll use the numpy load text file and we'll say numpy.load text and we'll pass in our raw data. And then we'll just say the delimiter is equal to comma. And we'll call this to output our dataset. And then let's just print our dataset. So here's the preview of the first row of our dataset. Now coming to cell 14, we need to isolate predictive variables from this dataset. The variables that would describe the word frequencies are standardized on the same scale, where other variables have different magnitudes. The reasonable thing to do here is to only analyze 48 features that describe word frequency counts. The side benefit of this is that there is no pre-processing requirement. This is our predictive dataset and we'll call it X. So now let's isolate our target variable. Again, this variable labels the records in the dataset as either spam or not spam, where spam records get a label of 1 and not spam records get a label of 0. So we'll call this Y. Now in cell 11, let's break up our dataset into training and test sets. To do that, we are going to call the train test split function and we'll pass in our X dataset and our Y variable. And let's just break this up in an 80-20 split. So we'll say our test size should be equal to 0.2 and then we'll set a random state here of random state equal to 17. So now let's come to cell 18. Now that we have broken our dataset into test and training sets, the data is comprised of continuous variables that describe frequency count of words. Multinomial naive Bayes is a great candidate, but we could also try Bernoulli's naive Bayes with binning to convert the frequency count to binary values. So let's try that first. We'll call this burn NB and then we are going to say burn NB is equal to Bernoulli and we'll pass in the parameter that says binarize is equal to true. So what this will do is it will perform the binning. And then let's call the fit function and we'll pass in our data. And we'll just print this out to get an idea of the model parameters. And then let's also do a test to summarize the model's accuracy. We'll create a variable called yExpect and we'll set that equal to yTest. And then we create a variable called yPred and we'll call the predict function and pass in our xtest data. Lastly, we'll print the accuracy score of this model. We need to call the accuracy function, and it's going to be the accuracy score, and we'll pass in our y-expect and y-pred. In the output of cell 18, what we see are the model parameters, and then we also get an accuracy score. So we are getting an accuracy score of about 86 for this model. Now in cell 19, let's see what we get with a multinomial naive-Bayes model. In this case, we don't need binning, so we are going to remove the binarized parameter, and then we are going to be calling in the multinomial naive-Bayes. As you can see, here we are getting an accuracy of about 88.1%. This is going to be a little better than our Bernoulli's naive-Bayes model, but since our dataset features are all numeric, we could try out the Gaussian naive-Bayes classifier. So in cell 20, we'll set this up for Gaussian naive-Bayes, and we can see that we are getting an accuracy of about 82% over here. Based on this simple evaluation, we can see that the multinomial naive-Bayes model is scoring out with a higher accuracy. Let's see in cell 21 if it is possible to improve our scores of our Bernoulli naive-Bayes model with trial and error. So I went ahead and played around with this a little bit earlier, and I was able to find that if we set the binarized parameter equal to 0.1, we get optimal results. And you can see now that we've gotten our accuracy up to 91%. So this makes Bernoulli naive-Bayes the best model of these three. This also points out that how important it is to adjust your model parameter settings to get the best performance from your models. So this ends our lecture 3.